Yeah, hi people. Nice that you're back. This week we have a very interesting topic and we will talk about Realtime Sanitizer. It's a very nice tool that can help you to understand how Rust actually works under the hood, which system calls are getting called, and obviously to write real-time safe code. So let's have a look at it together. Here you see the official GitHub group Realtime Sanitizer with all the repositories. You see the original project is for C++. Then there's a Rust wrapper and there's a Swift wrapper that is currently being worked on. I know the two guys that were developing this project. I met them at Audio Developer Conference in England, and they gave a talk about their progress to implement this into LLVM. So with LLVM 20 that is already released by now, Artisan or Realtime Sanitizer is an official part of LLVM, so it can use in every LLVM language. And I helped to bring this to Rust. So here's the Rust repository. We can click on that and just add some basic language extensions, some basic macros to make it easier to use the sanitizer in Rust. Here you see how it actually works, how you can use it. So that's mainly this non-blocking macro that you're using. Currently it's only working on Linux and Mac OS because Realtime Sanitizer itself does not work on Windows. But I hope it will extend soon. For now, if you want to use it on Windows, you have to use it in WSL or something like this. You can add it like this to your cargo toml, and by default it is not enabled because you don't want to have Artisan enabled in your production code. You have to call enable yourself. Either just enable it here, directly add the enable feature. If you just want to use it for testing, you can just always enable it, or you add a feature like this to your code, so you can call the Artisan feature just in cases here like this, just in cases where you actually want to track for it, for example in CI/CD. Yeah, it builds a C++ library in the back. It builds this part of LLVM, so it downloads some source files from LLVM. It's only a tiny bit of LLVM, so it doesn't take too long, but it might take a few minutes on Mac OS. On Linux, it's usually a bit faster. But you can also just store this pre-built library on your system and set this Artisan library path, and you never have to rebuild it in any project. Yeah, that's mainly this README. Let's just have a look at it in code. It's very interesting. So let's get started. I just created an empty project, right, with this add function. It gets added by Rust automatically when you create a new library. And now let's see how we can actually add Artisan. Cargo add Artisan standalone. It's called standalone because there is the hope that Artisan gets also implemented into Rust directly, into the compiler, at least in nightly Rust, and then just to defer if you're using this official Artisan or using the standalone version, right? So let's add Cargo Artisan standalone, and you already see here there's the feature enable that is not enabled right now. You can check here. Here we have Artisan standalone. So one option now is to add this feature. Where was it? Here. And the other option is just to always enable it. What we're going to do here, because we don't build any production code. For this, you just say cargo add Artisan standalone, and then features enable. Let's see what it does. Oops, this didn't work. Discard this file here. So it just adds this enable feature here, yeah. And now you're guaranteed that Artisan is actually enabled. So let's just test it on this add function, for example. You just add the non-blocking macro. Wait, non-blocking. You can also import everything from Artisan Standalone, then you have all the macros inside of your project. And let's give it a go. Let's just run this project. Here it builds fast because I already have the pre-built library on my system. And you see it works. That's fine. So, sorry. So just adding two numbers and returning it is obviously real-time safe. Now let's have a look at some more complex operations, right? So for example, let's try if it actually works with an allocation. It's not allowed to allocate memory in a real-time process, and let's see how that actually looks. So we remove this stuff here and just allocate a basic vector with 16 zeros. So let's see what happens if we call this. Run the project. And you see it crashed. So that's interesting. Let's see which error message we got. Scroll all the way up and you see unsafe library call, Realtime Sanitizer, intercepted call to realtime unsafe function calloc in real-time context. So we see a bit what Rust is actually doing under the hood, right? So this was calling calloc because calloc is for allocating zeros. And we wanted to have 16 zeros. If we change this to 1 and rerun the test, you see that now it was calling malloc. Malloc is just the allocator for uninitialized memory. All right, what can we do next? Maybe let's check how it works when we don't allocate, but just use a static array. Yeah, static arrays are on the stack. It's not a static array, actually. It's just an array in Rust. So this is memory on the stack and not on the heap. What happens if we create this? No call, no system call. Everything is real-time safe. And the cool thing is now we can actually even clone this. Let's call it data2. We can call the clone keyword on here and just recreate it as often as we want. And nothing happens. So using those types of arrays, you can just create them anywhere you want. You can move them around, you can go them. You're basically safe with it. Yeah? Nothing can stop you. So that's pretty cool. I think it's a really, really amazing tool to have to analyze how Rust works. Let's get a bit more interesting stuff. So for example, we check how moving works. Yeah, we have some data here. That is a vector. And we do something in here with it. And now let's, I don't know, let's just call this something else. And now we create the vector outside here. That is totally fine because we are not in a blocking context, right? Only what is inside of this function should be real-time safe. That's why we add this non-blocking macro. Everything we do here does not need to be real-time safe. So we can allocate our vector here. And then move it inside of the function. Yeah, and this should actually work. So you see if I want to use data here, it doesn't work because it says used of moved value. Yeah, it is not existing anymore. So by receiving data here, this function now owns data, and there is no copy made. So that's interesting. In C++, this would actually allocate new memory because the stuff would get cloned inside of here. But in Rust, it's really just a move of ownership, and the vector stays at the same position. No memory is actually moved. It's just the responsibility about the object that is given away. So let's check what happens. It should be real-time safe to move it, but there might be another issue. Let's start it, and you see it fails. That's interesting. What happened? Aha, intercepted call to real-time unsafe function free. So, because this function now has ownership of the data, and it's not used anywhere afterwards, Rust thinks it's okay to drop data here. Yeah, so what is actually called is this. Yeah, you can also make it explicit. So this is what Rust is doing, because no one is using data anymore, so we can drop it. But freeing, calling the system call free, is also not allowed in real-time safe code. What can we do about that? We could, for example, return the responsibility again. Yeah, and just do data here. This will return the data object back to our test function. So now we can receive it again and can use it here. For example, debug it. That's cool. So now let's check if this is real-time safe. And yeah, it works. And here we can use our object again, our struct. Very nice. So now nothing, it gets freed here at the end of this function. Yeah, here it's calling now drop data. So here it is allowed to drop the data because we are not in a real-time function anymore. Yeah, that's the cool thing, because we have to do things in our audio plugins that allocate memory. We just have certain sections that run in the audio process, and only those should be checked. Yeah, that's why we have this marker here that we can put on top of the function. So what can we check next? Yeah, that's interesting. When we don't use our data object, so I remove this responsibility again. And now I run it. It actually works. Only if you give it a name here, it will fail. That's interesting. And this is because Rust will just optimize it away here. Yeah, the compiler, because it knows no one is actually using data. There's not even a name given to it. So I won't even move the object in there. And that's interesting. So no system call is now being done. Yeah, just if you wonder, my Realtime Sanitizer doesn't work or something, always use the objects, for example, to check if something allocates or frees. So another cool thing we could do is check that references are actually real-time safe. So what we do here is, it doesn't want me to delete it. So now I can here use the data object again and see what happens. Now we are taking a reference, and that means ownership is not transferred into this function, but it still lives here. So we can still use it afterwards. Yeah, we can still debug it here, because it never got transferred. It never got moved into this function. Here we just have a reference to it. Let's see that this does not allocate anything. So even here it does not get dropped. That doesn't happen, because it's a reference, ownership lies here, so it will still drop the data in here. Yeah, that's pretty cool. So references are always safe to use. Nothing can happen if you use a reference. Then we can check some other system functions. For example, we can make a little sleeper. We don't need any input. And we just want to call std thread sleep. Then we take a duration of, I don't know, let's just take some milliseconds, 10 milliseconds, and see what this actually does. Let's give it a go. And now you see it failed. So sleeping is not allowed. But what happened? Intercepted call to real-time unsafe function nanosleep. So this is called nanosleep, the underlying function. Interesting. So yeah, it still warns you when you sleep. What is pretty cool. Because yeah, obviously you shouldn't block and this is not allowed. Then we can check threads. For example, creating a new thread. Yeah? This works in Rust also in this thread library, but then we call std thread and spawn. That spawns a new thread and returns a little handle. The handle is just to wait for the thread that it actually closes. We won't use it right now because we actually want to see if the spawn does already something and not joining the handle. Let's run the test and see. Spawning a thread is not allowed. What happens here? It's called malloc. So this is allocating memory. That's interesting. And we don't see anything else because the program immediately crashes. Yeah. This is happening because we don't set the command. We can actually set a command to Realtime Sanitizer that it does not stop. Let's check how that is. We scroll down here and there you see the section artisan options. You will find all the options in this Clang documentation, but here's this example, artisan options equals halt on error equals false. If we use this, I start in terminal and then we run cargo test. We will see now the test could actually finish, so it didn't abort. And now we see everything that happened. So we have our first malloc that gets called. Then we have another malloc that gets called and another malloc. And you see it's doing a lot. Another malloc. And then after more and more and more, let's see when something happens here. We call pthread create. And this is the actual thread creation function, yeah? So you are safe if you use Realtime Sanitizer. It warns you really about so many things and at least about any system call. And then we have calloc finally, and that should be it. Yeah. So that's interesting, right? There's a lot happening under the hood when you start a new thread. Maybe let's check what happens if we create this thread outside and just join the handle. Yeah, so now we move the handle inside. That's our join handle that returns nothing. And now we just call handle.join.unwrap. Unwrap is just to see if there's an error returned. And now we transfer the ownership of the handle inside of our sleeper and see if this is real-time safe. And you see, no, joining is not real-time safe because it's calling the system thread pthread join. Very interesting. Yeah. So all of this, please don't do it in your audio thread. Just do it outside and then send stuff into the thread. That's totally okay. But don't start or end this thread. I think also HTTP requests, stuff like this is not allowed. But let's look at another functionality of Artisan, because if you want to do something just for test cases inside of your function, you can temporarily disable the Artisan check. This is quite interesting. And this is called scoped disabler. And everything that you put inside of this field here won't be tracked by the sanitizer. Yeah, we can even return from this macro, so we can use our handle here. And then let's remove this here. Yeah, and then do the same for join, because joining is also not allowed. And see if that actually works. And you see now it didn't warn us because we did all of this in a scope disabler. That's also cool if you want to allocate some memory spontaneously just to do a test or so. And also for false positives. Yeah, if you do something where you know it must be real-time safe, or I have to do it in here, there's just no other option, then you can just disable this real-time sanitizer. And now we also have to free our data, drop it in here. And then also this will work. Great. Yeah, if you don't do this here, dropping the data at the end, we will probably have this free, we will have the free function again, because data gets dropped here by the compiler, or just because it's not used anymore. So what else do we have? Maybe let's check debugging. Yeah, we want to debug just a value. Let's remove this. Debugging is also not real-time safe because write is getting called. And that's exactly the same as for print line. Print line is not real-time safe. You will see calling this also calls the sys function write. Now let's check maybe an assertion, because assertions can be quite tricky. You want to assert here that a is smaller than 5. And now you run your function and you won't see it, because the assertion now tries to print. It tries to print the error. But as now the program crashes, you think, damn, my it's doing something. I don't know what's wrong here, because you don't see the actual error. And then you could do something like this, scope disabler, and just run the assertion inside of here. So if this if the assertion hits, it crashes anyways, right? So it doesn't matter anymore that we write. And then you actually see what was the problem here. Assertion failed. Or you just run Artisan without stopping, without aborting. All right. Another great thing is that you can specify own blocking functions. And this is nice if you have something, my own blocking. If you do something that cannot be tracked by Artisan. Yeah, there are things, it's not perfect. There are things that can't be tracked. For example, we just do a loop here that runs forever. this is definitely not real-time safe because we literally block forever. Yeah. Let's run this in our non-blocking thread, non-blocking function, and see what happens. Now we call sleeper again. It's running the test now forever. Doesn't stop. So you see here, we stopped it by hand. Also, you see this maybe better when you run cargo test here. It's running the test, but it never really stops because we loop forever. But yeah, Artisan cannot warn us. That's why if we know that we do something like this in a function, we just give it the blocking keyword, and then we are not allowed to use this in our real-time thread, okay? Just press play again and see now Artisan warned us, and it even gives us the name of our function. So call to blocking function my own blocking in real-time context. That's really, really cool. So with those tools, I think you are so much safer in actually writing code. And you can also use this in C++, right? Not only in Rust. Let's see how a Mutex Lock works as the last thing. A Mutex is interesting. Yeah, it's for multi-threaded access. So for example, if you have some data that you want to access in the UI and in your audio thread, you could use a mutex. You shouldn't in many cases because it is blocking. It can be blocking. There are mutexes that are kind of real-time safe. It depends a bit. But this default mutex is dangerous, and we can track this here as well. So let's just create a state with a new mutex and just give it a number. Yeah, so now we have a mutex of i32. So this mutex can be accessed from many different threads, and it's safe to use because only one thread at a time can have access to this state inside. And that's the cool thing. In Rust, we cannot have multiple mutable references, but a mutex doesn't need to be mutable to be changed. And there the guard is for, so we call state.lock.unwrap. Yeah. And this will return the guard. And with this guard, we can now access the value. So we can say, for example, guard plus equal 1. The guard has to be mutable, but not the state. And now this is pretty cool. That works. We can mutate this immutable state. Yeah, that's great. And Rust keeps us safe here because if another, or the mutex keeps us safe because if another thread tries to do the same thing at the same time, only one is allowed to access it until it's finished, and then the second thread can continue, right? So that's why it's dangerous, because this could wait for a long time and block your audio thread, and you have some crackles, or the autonomous vehicle drives against a wall because the sensors didn't update fast enough. Yeah. So let's see what happens here. If we call this Mutex Lock, there's something interesting happening. It does nothing. And this is because this could be actually real-time safe, because we are locking the state, but no one else has the reference, so it does not have to wait here. And this is something special in Rust, because the Linux implementation, we on Linux here, of the mutex is using a kind of a combination of a spin lock, and if it cannot get the lock after a couple of spins, it will do a system call to wait or to block the thread a little bit until it spins again. So if we just do that, in Linux, it's totally fine, because we just get into the spin lock, it tries to get the lock, and if it can acquire this lock, what it can here, because no one else locks it at the moment, blocks it, we can just do this. And we didn't need to wait, so this is actually fine. And the system call gets called after a certain amount of iterations. So this would be, in some cases, fine to do in a real-time thread. But if you're on macOS, you can try the same code and it will fail because macOS is using always this pthread lock from the operating system, right? So in Linux, it's a special mutex. On macOS, it's the system mutex. So if you run this code, you will see actually also some allocations at the first time you lock, and then the actual pthread call. Now, there is an example here inside. If you go to examples and to Mutex, I engineered something here that warns you on Linux as well, because we have a state and we have a process function that gets this mutex, locks it, and tries to increase it, the value inside of the mutex. And then in our main thread, we create the state, then we lock it in our main thread, clone it, and move it into this new thread where we call the process function. So now we have two threads that both try to hold the lock and update the value. And then we even wait here for a second just to ensure that on Linux as well, the spin lock runs to the end and then tries to call the system function. So yeah, this example, you can try it if you're on Linux or on macOS, it will work as well. It will actually, Realtime Sanitizer will actually warn you with this example. Yeah, that's basically it. We can look at this another time again with some more complex stuff or in bigger libraries. But I think it's a great tool that will help a lot of people get started, learn how Rust works, learn what is real-time safe, what is not, and hopefully will make the real-time world a safer place with some airplanes or cars using Rust in the future. Yeah, great that you were listening. Sorry for my voice today. I'm still a little bit sick. That's why I missed a week of the videos as well. But I will continue. I'm here. And yeah, let's continue to learn Rust together. And I'm happy if you click the subscribe button or support me. But anyways, I'm happy to talk about this stuff. So see you next week. And keep on learning and writing code. Bye-bye.